Good morning, or good afternoon, or wherever you're watching. It's Keith from Sunsynk. It's a beautiful day. I'm in the United Kingdom this week, and it's absolutely gorgeous. This is a presentation I done a couple of years ago, and I'm feeling it's about time to do this presentation now. So I hope I'm not going to bore you, but I'm going to cover a lot of topics. I'm going to cover how inverters function, or how Sunsynk inverters function, the advantages of a Sunsynk inverter compared to others, and I'm going to cover a lot of other topics. So get yourself a cup of coffee or a cup of tea, sit down, relax, and I hope it's useful. I hope you get something from it. I hope I'm not going to bore anybody too much. But let's talk about our inverter, Sunsynk. You know, we've been at it a long time. Sunsynk have been making inverters. Wow, over 20 years. We've been at it a long time. We're not new kids on the block. We've been around a long, long time. So we're not being sort of, you get a lot of these new companies being in 1 or 2 years. I'm not going to mention names, and then suddenly they know everything about inverters. They know everything about everything, but they've got no experience. They don't understand the issues that you have in the past and the problems you learn from your experiences. So I always find it amazing how companies come along and know everything, and they're suddenly super duper experts, but actually not trading very long. Anyway, we've been at it a long, long time. Let's talk about our inverter. Our inverter is IGBT based. IGBT, Insulated Gate Bipolar Transistor. It's a transistor. It's bipolar transistors been around since the sort of 50s, 60s. I'm not too sure. I'm sure somebody will correct me with the date when it was actually invented. But the bipolar transistors they used to have in little transistor radios when you moved from vacuum tubes valves, and so it is the very first transistor. Insulated gate is a little bit different. It's a very different type of thing. So it's maybe a little bit a cross between a MOSFET and a bipolar transistor. But I'm not going to go too much into that at the moment. Main differences between IGBT and MOSFETs. Many inverters, especially the sorts of budget products, use MOSFETs. All of our stuff is using IGBTs. There are some advantages and disadvantages. So advantages of MOSFETs are listed below. So that the sort of MOSFETs have used a greater efficiency, low voltage. It has no gate current, so high impedance. It can switch. This is why people use MOSFETs. But MOSFETs are very good for what they call closed circuits, like sort of amplifiers. A lot of amplifiers use MOSFETs because it's a closed circuit. With an inverter, you're connecting it to a house load, which is a complex load, and there's lots and lots of things going on to it. So a disadvantage of MOSFETs is they're very susceptible to electrostatic discharges, and they can be unstable, certain problems, and I'm not going to go too much about it, but there are certain issues about it. On the other hand, IGBTs, disadvantages of IGBTs, well, they're expensive, they cost much more money, and certain latching problems, and there's certain lots of other issues, but they're used everywhere now. They're used on power circuits, and they're very, very good. So all I can say is we use the best. I'm not going to go too much of that. Okay. So let's look at our inverter, and this is the crux of what I'm trying to explain on this video. So our inverter is a bidirectional inverter. Now all the Sunsynk storage hybrid inverters are bidirectional, the pure bidirectional. Nowadays, I'm looking in some videos and people were talking about, mine's a hybrid. They're not hybrid. There are string inverters with some sort of complex battery charging system that takes the solar from the solar panels and charges it into the battery. It's not a hybrid inverter. Hybrid inverters, the Australians would call it a multi-mode inverter. So hybrid is a fairly new, meaning mixture of two technologies, but they're not the same as what we produce. And so obviously companies are trying to race to the bottom and trying to get cheaper and cheaper and cheaper. And everything's hybrid because hybrid is the buzzword. But they're not the same. So the better way to describe is, our inverter is a bi-directional inverter. The inverter goes both ways. So you have inside the inverter, you have an AC bus. You have a DC bus. And these are very, very important. So the DC bus is where the batteries connect to and where the output of the MPPTs go to. Everything's on the DC bus. The AC bus is where all things to do with the AC are connected to, which is the load connection, the grid connection, the auxiliary connection. Everything is on the AC bus. And the inverter sits in the middle. But the inverter can actually go both ways. So the inverter can charge the battery and it can discharge the battery. It can reverse. The same piece of kit goes both ways. And that's what makes it absolutely amazing. So let's just look about the inverter. And I'll go through what some of the functions about it. One of the things about it also is efficiency. Because we're just using one unit to charge and discharge, then you've only got one set of losses. The more DC to DC conversions you do, so some people have batteries with DC to DC conversions every battery. You're what they call a round trip efficiency. So by the time you charge the batteries and you discharge the batteries, besides there's lots more things to go wrong, the losses, every time you do this, you do get some losses. There are some losses. Of course you get losses, because you get losses to do with the volt drop across a transistor or an IGBT. There's a volt drop, and that creates a loss. So let's look here. This is most of them using MPPTs, maximum peak power tracker, common name. Some of them use slightly different words, but they all call them MPPTs. The reason for an MPPT is to maximize the efficiency of the solar panel. Now, a very simple, crazy example, a long, long time ago, you used to have solar panels and you get a 48 volt solar panel and 100 watt. And you could connect it directly using PWM, pulse width modulation, directly to a car battery to charge it. And it would charge the car battery. But that panel will change its characteristics. 100 watt at 48 volt, okay, you could do the math. It's 2 amp. So if I'm calculating correctly on the top of my head, yeah, 2 amp. So at 100 watt, 48 volts, it will charge at 2 amp. You then connect that solar panel directly to a car battery using pulse width modulation, so it's switching it off and on, and it will still charge at 2 amp. Because if you short a solar panel, it will be 2 amp. So they will call it the short circuit current, which is the maximum current a solar panel can deliver, and it will be around the 2 amp. So you put 2 amp at 12 volts. So 2 amp at 12 volts actually is 24 watt. A little bit higher because the charge voltage of a 12 volt battery is about 14.5 volt. So allow a little bit more. So it'll be a little more, but roughly 2 amp. And so therefore you actually have changed the characteristics of a solar panel from being a 100 watt solar panel to becoming a 25 watt solar panel. It's a quarter. Where's the watts gone? That's just a characteristic of the solar panel. You know, solar panels have been around a long time. Some information used to call solar panels solar batteries. From my memory, it was invented by Bell Laboratories. The first solar battery. They're ridiculously expensive, and most of them are used for satellites. And they discovered that these solar batteries will start working and keep working and working forever. And that's the beauty of solar panels, especially you've got these silicon solar panels. They should last, providing they're produced well enough and the sorts of connections are good enough, then these things should last a long, long time. So this is a bit on the MPPT. So looking at the other parts about it, so at the moment is you have the MPPT, it will charge, it can charge the battery directly. So the MPPT can charge the battery directly, but also the inverter can charge the battery. So the battery can have two sources of charge. One of the things we look at, and in fact I take it a little bit out of order, but we have a common AC bus. So we have one common AC bus. The AC bus, what prevents it to sending the power? We use what we call a CT coil. So CT coil, which is a current transformer, prevents the power going back from the AC into the AC. It controls the export. We don't actually use a changeover relay. So this is probably a better description than the first one here. And this shows you an overall view of everything. So we have a common bus here, a common AC bus. So the grid, the generator, the load is connected on here. There's no relay. You can see actually, there's no separate relay. We don't actually have a changeover relay. So therefore, if you change over from AC to DC, the inverter, it's instantaneous. I know some of our competitors say, oh wow, we've invented 0-second, millisecond, microsecond, gazeng-second changeover. But there isn't a changeover. There isn't actually a changeover because now it also depends on depending on whether the inverter is in discharge mode or charge mode. Because if it is in discharge mode and you lose your AC, your grid relay will open because it has to for the anti-islanding in a fraction of a whatever second. And that gives you anti-islanding. But your power to your central loads will remain because this could be discharging to the essential loads. So therefore, it is a zero changeover. Zero. And that's the same, we've been doing it for years and years and years. It's nothing new. And I think I've done a video explaining it and showing it. We haven't sort of we see some people say, oh, we've invented the zero changeover and it's a big deal. Well, yeah, they caught up with us. The thing is, though, with zero changeover, if the inverter is in a charge mode, so the power is going into there, and it is a different function, you lose it, you have got a very fraction of a second, very quick, while this changes direction. So you do use something which changes direction. You have to use a relay for safety reasons. So there is something. But when it is in discharge mode, it's zero changeover. It's impossible for changeover. And if you look here, you see here on the grid flow, what prevents it flowing back into the watt meter, this is the watt meter which connects to the grid, is to use this good old CT coil, current transformer. And the current transformer detects any export back here into the meter, tells the inverter, and so the inverter adjusts the voltage. Because when you've got two voltages, and you've got the voltage of the grid and you've got the voltage of the inverter. And if the inverter voltage is slightly higher than the grid, current will flow. If the inverter voltage is slightly lower than the grid, current will go there. And by adjusting the voltages just ever so slightly, and that's how you control the export and the import. It's controlled by you control it by the voltage, very slight differences. And you can sense this on the transformer. So that's how it works. And what you actually have is you have on here on your grid, you have what you call your non-essential loads, so which is connected to your grid. So you can have power flowing, if the grid relay is closed, you can have power flowing from the MPPTs, flowing from the battery into the grid, into the auxiliary, into the essential loads. If you then have a problem, if you have, say, a failure, a fault, and you lose grid, you have to open the grid relay. It must open, because it's a legal requirement. The grid relay opens, but the load relay will carry on supplying. So you've got constant power. And as I said before, it's instant. There's no changeover. It's a 0 second whatever changeover. It just carries on flowing. And that's something that we did many years ago, before some of these millions of companies. I don't know how many. It's a free market. There's lots of companies. Everyone has got. It's a free. We haven't got a monopoly on making them, but many companies are sort of catching up and looking at the similar technology. We have this other one which we call a generator or an auxiliary load, but all it is a relay. It is connected to the common bus, and so if this relay is closed, now the interesting thing is. And in fact, if I've got a drawing showing it, and this is maybe a little bit interesting here. If I've connected a generator here, so this relay is closed, the generator now is powering the essential load, so the power's there. But also the inverter now is in charge mode because it needs to charge the battery. So the generator has to power the inverter, which is charging into the battery, and it will power the essential load. So if you connect the generator like this, the generator has to be big enough to take the whole load of the essential and the inverter, whatever you set it to charge at, so it can charge the batteries. It's got to power both. So you generally need a generator which is bigger, much bigger than the kVA of the inverter. So if the inverter is, say, a 10 kilowatt inverter, then you probably have to go to like a 15 kVA or a 20 kVA generator to make sure its tolerances. You don't always have to do that, because there are another way you can do it when you connect it to the load side using ATS, the automatic transfer switch of the generator. And when you connect it onto the load side here, and then you have your load flowing through the generator, then you can control the size. You can use a much smaller generator. But the disadvantage is, if your load is too high, then you could fall in danger of flattening your battery completely. So having a generator which is big enough to take the load and charge it, you'll never flatten the battery. So doing it the other way, where you're using a much smaller generator, it will work, and it can definitely charge the batteries. But be aware, depending on the load size, the side that you've got, so it is different. Wow, this is a little bit more. This is using it as a smart load. This is showing the configuration. So here we're showing the batteries discharging here, and the smart load is when the battery voltage reaches a certain voltage, as we call it, a hysteresis. So if the battery on the state of charge, the SOC, which is actually a voltage measurement from the battery itself, but we call it the SOC. So if the SOC is 100%, and we set it to come on the smart load or the auxiliary, and then it will start to discharge. It will start to discharge through this. And then we might say, well, when the battery drops to 80%, it will stop. Now, there's a massive advantage for this. Now, I can show some of the videos, because there are devices that say, oh, we've got power diverters. So when the sun is shining, if there's not enough power being drawn from the panels, then it can divert the solar panel to a hot water geyser. The problem with doing it that way is you're powering it on a variable signal. So 1 minute you've got a kilowatt, next minute you've got 500 watts going to the hot water, 100, whatever. It's up and down, up and down. But you know, a hot water tank, you have a thermostat on it. And the thermostat actually is a bimetal strip, which actually works, and I use the word hysteresis. It's got an on and off mode, and there's a level in the middle. So with hot water tanks, they need all or nothing, because with a hot water tank or a water geyser, when the element is cool, the resistance of the element is different to when it's hot, because it changes. And so therefore the efficiency, if you can power it completely and take the power off and on in a hysteresis mode, it will work much better. It's much better. And so therefore the Sunsynk inverters all have this built in, and you can run this hysteresis, and the efficiency heating a solar or hot water geyser using a Sunsynk inverter is much better than anything else. And you can see what happens is here the batteries discharge through the inverter. So this is the DC bus, the batteries are on the DC bus, the inverter is discharging, it goes onto the AC bus, and the AC bus the relay is closed, and it's powering auxiliary loads. And you can see exactly what is happening here. It could be in this particular mode, and I've shown here. It could also be taking some power from the grid if you choose. You can choose that. So you might be on this particular mode. You might be, there's lots of options what you might be choosing. So one of the things here also is you might select, say, if grid is present, I want the auxiliary to operate. Or if grid is present, I don't want to operate. You have a choice. It's a tick box on the inverter, and it's a very simple thing to do. Looking at AC charging, I'll move the other way. Right, okay. So AC charging, I'm taking my power from my AC. Okay, still power my essential load. This is on the AC bus, but I take so you see here, and I take some of it goes to the grid, goes here. You see that goes here, and the AC goes into the inverter. And the inverter is now operating in reverse, and it's coming out of the inverter and it's going into the battery. So you can see the flow on an AC. So the AC come here from the battery through the grid relays closed onto the AC bus in the inverter, through the inverter itself, out of the inverter the other side, and charge the battery. It is very simple. But is it so simple? There's no separate charger circuit. You don't have because it's super duper efficient. Efficiency saves you money. And having one device, one piece of kit, massively improves the efficiency. You get some of these sorts of stackable, got lots and lots of inverters everywhere, and they DC to DC converters, buck converters. They make them a buck converter or a boost, buck and boost. There's different type of thing. Buck is where you drop it down, boost is where you bring it up. But they're nevertheless a DC to DC converter. Every time you convert the energy from one to the other, you lose a little bit of power. And often look at what they call round trip efficiencies, because this is something that people don't think. And obviously lots more to go wrong. But the beauty of this is so simple. And you can see how it charges from the watt meter here. Come the CT coil, obviously seeing what's going on. Essential loads is this is your consumer unit here. And then through the inverter, relay is closed here. I haven't got anything auxiliary, but I've got my essential loads here. Through the actual inverter itself, onto the DC bus, and the battery is connected to the DC bus. And that's simple. And that actually is the same with all of the inverters, whether you're looking from a LifeLink, a little Links inverter, or a small, whatever inverter you're looking at, it all operates the same way. So it's a very simple way. Discharging the battery, same thing really. What I was showing before, it comes out, and you can see here into the essential loads, and you can see, now what we're showing here is actually showing the power coming from here. But in fact, this could actually discharge to the consumer unit. So it could discharge here because we can control by the CT coil. So we can actually discharge either onto the local, we can either have essential load only, or we can discharge to the home load, but with 0 voltage export. So you can see on this sort of here, discharge just directly to essential load. And this relay would actually be open when basically if you've got no power, or you're off grid, and so therefore there's nothing going to the essential load. There's no power here. There's nothing going. Relay is open. This is all open, and just the power is going to the essential loads only, and the inverter is working super duper efficiency. Now, obviously, if you've got any sun shining, this will contribute towards the battery thing. This will also flow from the MPPTs. So when you're operating like this and you're off grid, you want maximum efficiency. Because if you're going to start suffering from, it's all having something that's nice and pretty, but efficiency is important, absolutely important. And this is something we always talk about, and we think about, well, we can make it do this, we can put efficiency, and this is one of the things about it. This is what I've been talking before about MPPTs. And you see, the MPPTs working together. The MPPTs can be charging the battery and converting, sending it out to essential loads off the MPPT. So at that point here, the MPPT is powering the essential load direct, and you can see, and it's also powering the non-essential. So if you've got a nice bright sunshiny day, you might just charge. Your MPPTs are producing 10 kilowatt. And then you're loading your non-essential loads, maybe 5 kilowatt, throw the other 5 kilowatt in the batteries. That's really important. It's really important because that differentiates between string inverters. String inverters is the Americanism for series. We used to call series, but string inverter is basically you put lots of panels in a series, in a string, and you plug it into the MPPT. But they don't have a battery. The nice thing about this is your surplus power going through the inverter here, which is powering your essential and powering your non-essential, and your surplus power, your extra power, rather than wasting it, we're not sending it back to the grid here, we're putting it into the battery. And this is how it works. One unit here from the MPPTs, maximum peak power trackers, number 1, MPPT number 2, both filling up supplying our load, both essential and non-essential. This is the AC coupled. This is your AC grid, supplying both and putting the balance the energy into the battery. So that's something how it functions. A lot of people think it's all magic, and they'll say, "Oh, look at this, it's beautiful." Well, but I think it's important to get, as an engineer, I think people need to get a good understanding how it functions. So I was trying to explain a little bit about the functionality of the inverter. Solar panels. Well, we talk about MPPTs and talk about solar panels, and this is something that people think. We put 450 volts, voltage max, Vmax 450. Now, many of our inverters go way above that, and some of them over 1,000 volts. This is your voltage, your string voltage. We always suggest if you have if your inverter says 550 maximum string voltage, try to keep it below that, because solar panels, and you'll measure it and you put them up on a beautiful summer's day and you say, oh my God, there's a lot of sun produced, and it's going to give me 400, it's going to be 500 volt. We're okay, we're all happy days. But one thing you need to understand is silicon solar panels can work more efficiently when they're cooler. And so you'll get what winter sun. So in the winter, you'll get, and today I'm looking at, wow, I'm looking through the winter, you can't see, but it's a cool day today in the UK, but the sun is beautiful, producing lots and lots of energy. The problem is the voltage goes up, and it's very easy to take your voltage over your maximum voltage, because it's all about your voltage. Everything's about your voltage. You don't care about anything else, but care about your maximum voltage, because when your maximum voltage goes too high, then you can damage the power converter. And that's what you've got to be very careful of. And it's easy to say, oh yeah, but I've measured it all and the inverter says 550, so I've set mine to 550 in the summer. But come the winter, that could go to 650. So we often say 450 is a good voltage on a 500, 550 volt Vmax. And of course, take it up, because obviously now this video was done a couple of years ago, and also video presentation, sorry, the video's done now. It's actually wow, it's 9th of April, and on a sunshiny day in the UK. But Vmax is very important, and I can explain a little bit more about that. You know, let's look at a 5 kilowatt MPPT. Okay. So this is very important, okay? And so the amperage are going up. So we're showing 22, now 26 amps. They're much higher. But you look at your maximum amperage, your MPPT. Now you may have an older one which is 22 amps. This is when this was done, but I can tell you some of them are 40, 50, some of them much higher. So depending on the unit. So this, I'm just using this as an example at 22. So please don't say all Sunsynk are 22. They're not. None of them are that now, because everything changes. But if you look at the maximum 22 amps, and this is quite important. So 22 amps at 450 volt is almost 10 kilowatt. We're talking about a 5 kilowatt MPPT. 5 kilowatt MPPT can take 22 amps, can take 450. Is that? Of course it can't run at that. They're the parameters. If you run it at that, it'll be a 10 kilowatt MPPT. It won't be sold as a 5 kilowatt MPPT, it'll be sold as a 10 kilowatt MPPT. And that's the unit, that's the coils, that's what everything you can dissipate. So that's very, very important. It's very important to realize that. And that's why we say 450 volt. Look at that, look at those two figures, multiply the two figures, we'll give it you. But that's not actually the case. You know, if I using my plug socket, my main socket, it's got a 13 amp fuse. Probably if there was no fuses, it could probably deliver 10,000 amps. I don't care. It's whatever for a very fraction of a second, the wire will limit it, and the wire will melt for sure. But that's why you put fuses, to prevent the wire from melting. But it's got the potential current's very high. But even if you say 13 amps, and I plug in my phone charger that draws half an amp, the 13 amps is not going to blast the car charger, because it's what it pulls. So that's important. And we'll go through that a little bit, explain a bit more. So, as I said before, 22 amp, 450 volt, 10 kilowatt. This is, but it's not. It's not. So to optimize, we look at optimize. So if you want to optimize, you're looking at the size. So optimize, if you say, right, I want to deliver 22 amps, because that's the maximum thing. 22 amps is the maximum power that panel can deliver. But you look at your voltage. So 5 kilowatt divided by 22 amps is 227 volts. So it's the lowest voltage that you can operate the system at. You don't want to go below that voltage. So there's two voltages to consider. Oh my God, we've got two voltages. We've got an upper voltage, 450, but you also consider a lower voltage. Because if you go below the lower voltage, the lower voltage that you can send. So for example, if I've got a solar panel that's basically can deliver much higher ampage, and I set it to, then you're going to cause damage to the MPPT. It causes heating to the MPPT. So here we've got a 5 kilowatt array with a voltage 227 max. So here your lower voltage and your upper voltage. You want to be somewhere in between. You don't want to go lower than that. You don't want to go higher than that. So when you calculate your array, it's important to consider something in between, because that will give you a highest efficiency. So I show this here. What often happens is inverters they often say will throttle off if you want to supply more power than the MPPT is designed, and then what will happen here? It will flatten, because if it carries on going like that, then the MPPT is not a 5 kilowatt. This is an example of a 5 kilowatt. It's not a 5 kilowatt. It's a 10 kilowatt. So you just buy a unit with a 10 kilowatt MPPT. It's bigger, so it can't do it. So all it can do is it can flatten off here. If you're using an oversized panel, which you can do, and what it will do is it will flatten off longer, but in fact you will get more benefit of the energy, because here, if you look at the energy the energy is here, which is under the curve, is the power you're getting, and here you're going to get a greater power, so it'll expand the day. So if you're oversized, you can oversize panels. And often people say, oh yeah, but you can oversize panel. Of course you can oversize panel. And oversizing panel basically expands the day, and you can see from here. Unless the other thing is some of our inverters, for example, our 3.6 has a 7 kilowatt MPPT. That is a true 7 kilowatt MPPT. But if the MPPT is a 7 kilowatt or a 5 kilowatt, is the actual 5 kilowatt, oversizing just creates this, you will get this flattening here, but you will get the energy under it will be greater. So it's always worth considering it. So, but that's all oversizing is going to do. Right, that's enough for solar panels. I said I'd cover a few topics. RCD. Well, residual current device. When I was at college, we used to call them ELCBs, earth leakage circuit breaker. It's a safety device. It's very important. This is what the things look like. It's a Schneider one. It's not a very good picture, but here, this is one that's got a little test button. And I'll explain a little bit more about what it is, okay? So an RCD device is a residual current device. It's a life-saving device. It's basically, if I touch a live wire, it will trip because the circuit, and I'll explain why, but basically if the circuit is made between me and the ground, and then it's safety, it trips. It's purely a safety element. And so I understanding RCD and understanding about them, but inverters and RCDs don't always like each other. So this is an RCD, ELCB. There's lots of other versions. You've got RCBO. You've got lots of things mixed. They put combinations and they put them in everywhere now. And I see them plug tops. In fact, a long time ago, I was involved in designing them. I used to use a Motorola chip, a little Motorola chipset, but it detects an imbalance. So here we got a live feed. It goes into the RCD. It goes into the load. Power comes back out. Neutral. We got a circuit. The power going through the live is the same coming back in the neutral. We've got the same thing. I'm not going to go about what the difference between the live and the neutral, because they're both, which we'll talk about when we talk about sort of classification, but we talk about on normal single phase grid, and three phase was similar, but just look, it's on a normal single phase. Neutral earth is often the same thing. So here I may have a neutral earth bond, especially in South Africa. Some countries don't allow it, some countries do allow it, but we have some of them have a neutral earth bond. But nevertheless, the RCD is here, and the RCD is sensing at this point and this point before any neutral earth bond. Then this thing is balanced, and it happily runs perfectly. Now, if I have an imbalance, so here my live power going into the RCD comes out, and then here is my neutral connected to the load. Here's my neutral. If my neutral here, if I have an earth bond here, then that's going to create an imbalance, and therefore the RCD will trip. That can happen in lots of scenarios. RCDs have a trip current, so the power which it takes here is often rated in milliamps. Most houses in the UK use what they call a 30 milliamp trip. If you're using an inverter, many of the regulations say you don't necessarily need an RCD. Personally, this is my own personal choice, I would always use an RCD, maybe 100 milliamp trip, because there are, inside the inverter, we often use Y capacitors, and there are certain routes that might take the energy from to the ground using very small amounts, using Y caps and various things, and maybe from various routes or how the power is flowed. So I would normally go, personally, I would go for 100 milliamp, but it's a choice. I'm not going to convince that the regulations are a little bit depending on how it's wired, depending whether the wires are in the wall, they're exposed, and lots of things. So, but the point is, this is a residual current device. If the routing of the power is different, so it comes from here and it causes this imbalance, this causes trip. Long time ago, they used to be called what they used to call a Wheatstone bridge. It was a bridge network. And then when you got an imbalance on the bridge, you got a voltage in the center of the bridge, and it would cause a mechanical trip. And these things were purely mechanical. Now they're all electronic. And as I said before, we used to using with Motorola chips is another simple thing. So here you've got live neutral coming in. Here, if you have a fault, here this will trip on the inverter. The reason, because you've got to consider part of the issue where you're going to have tripping or nuisance tripping is to do with the earth neutral bond. And so therefore, if you have to make an earth neutral bond, so here I may have a bond on the inverter, but the bond can't be permanently connected to the grid because this will cause an RCD to trip. This is very simplified, and if you should really, if you want to know more about it, go onto Google. There's lots of explanations about it, but the most important thing is to understand what goes in must come out. If the same doesn't come out the RCD, it will trip. And there's lots of ways this could be routed. And you may have an RCD at your grid. Then some people, or your supply coming in, you put an earth neutral bond later on. That will cause the main one to trip. It's to understand how it's mainly to do with earth neutral bonding causes the problem. I'm going to talk about earth neutral bonding in a second. This is a little bit more of an RCD showing here, this slide here. So here I've got my RCD here, power coming in here, going into the inverter, and the inverter outputting into an RCD and into the load. So on the output, on the load side, so on the load side here, I've got an earth neutral bond here. That earth neutral bond will actually not cause that to trip because it's before it. But what could happen on here, if this relay is closed, this one could trip. So if I've got a direct circuit here at some point, this could trip. So it's very important when I've got this to disconnect this. You can't have the two, otherwise one will trip. This will happily protect, because on the output of the inverter, on the loading side, if I'm off grid, then I need to do an earth neutral bond, because if I don't, it needs to change the classification of the inverter. First time you're going to hear about this classification, class 1, class 2. Class 2 is they both the same potential. Class 1, so I've got a grounding. And most appliances in a house are class 1. And so therefore I must have this bond. Otherwise it can be a little bit dangerous. And this RCD can protect it. But I must disconnect this one. And we can do that with relays and various things. So that's quite important. So what I'm talking about here is changing the output of the inverter from a class 2 to a class 1. I can tell you this, absolutely tell you this. Not everybody does this. So many inverter manufacturers, many, actually output as a class 2 on the UPS, on their essential load. They don't actually have an earth bond. They don't have an earth bonding. So therefore, it can be dangerous. Now, if you're going to using a class 2 product, and maybe your hairdryer or what else, electric drill, is class 2. So class 2 doesn't have an earth connection. There's no earth connection. But my refrigerator, my water geyser, heater, they're all class 1 because they've got an earth. And that's important, because if you don't change the configuration, both at the same potential, and you will not detect an earth fault. An earth fault would not show up, it will not trip. So it's very important. Now, in fact, this is a video, I won't go on this, this is actually a video which I've done, and I'm not going to explain about it, but this is actually using a relay, an external relay. Now, many of our inverters now have it built in, but some of the older ones don't have it built in, and you have to use a relay, and that relay will operate. And the relay, the changeover relay only operates in certain conditions. So once you lose the grid, within a fraction of a second of losing the grid, it will make the earth bond connection from the load side very quickly. But it has to lose the grid first, and within a millisecond, it will make that connection, and therefore you're safe. You're safe. You change the classification. If you don't make that connection and it's not done, then it's dangerous, and you're going to be outputting, especially if you're going to be a whole house load on a class 2 inverter that's outputting onto a class 1 load. Not clever. So you have to do it. The other thing is when you remove that connection, so that connection must be removed just before you make the connection of the grid. So therefore the inverter has to have an intelligence to know when the inverter is going to be connected back onto the grid. One of the things to understand about it is when you're making that grid, when that grid connection is made, before it happens, one of the things that the inverter has to do, it has to synchronize. So the reason why it takes time, you say, oh, I'm waiting for the inverter to come on. The reason it takes the time is because the AC is running a frequency, the inverter is running a frequency, and they both have to lock. They have to synchronize. It's like when you're running a generator. When you're running a generator, the generator is running, and say, oh, my inverter is not synchronizing with the generator, because it has to synchronize. The frequencies have to be the same. If it connects and the frequency is not the same, then the result is bang, end of inverter, maybe end of generator, because they're just conflicting, they're powering each other, they're going against each other. And so that's very, very important. This is just talking about, we were talking about RCDs and the type A classification, 2-pole, 30 milliamp. But again, I was talking about using higher power ones in certain applications. So that's boring you, enough of that. Let's talk about batteries. Now, I'm only going to talk about low voltage batteries. I'm not going to talk about high voltage batteries, because high voltage batteries are a little bit different. And this is just a very simplified a very simplified thing. Never actually use unapproved batteries. Now we've got past the new regulations in the UK. Batteries are supposed to be mounted outside. I know the regulations have not come fully in force yet, but it could come. And there's lots of ways you can do this. But I'm just talking about a simplified thing, and presuming these things are outside or in a particular area. And the past regulations call for lots and lots of things, and it's important to ensure that your batteries can run. People say low temperature. Well, low temperature is important. This is why people think, oh, it's all about cheapest battery possible. I can buy a battery cheaper. It's not. It's a lot more to it than that. There's a lot more to it, and you want longevity. You want something that's going to last you. And many years ago, I'm a tradesman, you probably know, and I've been on the tools, and I used to buy, you used to buy an electric drill, and you do a job, and a few jobs, and suddenly the thing would break. Oh, this is rubbish. And go on and buy another one. And eventually, after 2 or 3, it was sinking to my brain. Maybe perhaps I should buy a better quality one, because I'm fed up of throwing these away. And if I bought a better quality one at the beginning, I've still got that. And so then I went to the tool shop. I said, give me the best electric drill. What's the best one you've got? Well, I need something that's going to last me, because I'm reliant on it. It's important. I'm relying on it. I'm relying on this. And I need something that's super duper reliable. Because if you're relying on something, I do suitcases. I used to buy, you buy suitcases, and you go on holiday, and you on a trip, and the next minute the wheel's fallen off, or it's burst open, your clothes are everywhere. It's let you down at the worst possible time. And you often think, get quality. Don't care what it looks like. I just want quality. I want something that's going to last, fit for purpose. So never use unimproved batteries. So looking here, it's a very simple thing. What very simple wiring here. We're using 35 mil cable. You are limited on 35 mil cables about on what you can pull from it, and there are certain requirements. But doing it like this, maybe we're looking at a 100 amp configuration, a simple 35 mil cable. You've got your fuse isolator, which is very important. And you might wire it in a very simple configuration. 2 wires are there, and then parallel off to a second battery. It's a very simple configuration. It has problems. One of the things you'll have is when you wire like this first battery will take more of the stress than the second battery because of the resistance here. It's not much resistance, but there is a resistance in these cables, and it will be slightly imbalanced. And so one of the things that people often recommend, and especially if you're looking, say, for drawing at 200 amps, is you will wire this way. And so you wire your stack, and your bottom battery, you can bring it back to the top. By doing that, you're taking off this one, you're taking off this one, and it will balance your battery stack a little bit better. This is primarily for when you lower voltage batteries, then the resistance becomes more important. So when you go in high voltage batteries, it's less important. It's important, but less important. But especially on low voltage, because the resistances make a huge difference. And you can see here, you can double up on your cable, you can double up and you can terminate both at the inverter or a junction box. Many of them use junction boxes nowadays. When these slides were originally done, we didn't have junction boxes, but we've got these amazing pieces of kit and these junction boxes that are superb. So this is one of the things. Fault codes, right? Everyone says the inverter's faulty because it gives a fault code. The inverter is actually monitoring not just itself, but it's monitoring the whole system. And it's very important. So fault codes is something that people should be always aware of. They're a diagnostic tool. They're a tool for checking about your system, to understanding how your system is functioning and to make sure everything is functioning well. They're a diagnostic tool. They help prevent fires. I won't go into this one. This was actually showing, about an arc fault, but I'm going to go through this or whatever. But anyway, we'll move on. Let me just go on to the fault codes itself. So fault codes. You see here, you'll get a screen, and even with our new push UI, our new UI or whatever, we do have screens with fault codes. But the fault code is a system diagnostic tool, and it's checking your solar panels, it's checking your batteries, it's checking the inverter, it's checking your cables, it's checking everything. And so fault codes are a pure diagnostic. If a fault code comes up, just say, it's the inverter's faulty. It's not. It is actually showing you there's something going around. So these are some of the common fault codes. FO3, ground fault detection. Okay, so ground fault. This is an indicator that it's caused by a faulty solar panel. F3. It's a solar panel. It's very rare, but if you get a solar panel with a ground fault, it can happen, and it will show up on the inverter. And people might say, "Oh, the inverter's faulty." It's nothing to do with the inverter. It's the solar panel. I've heard in the past somebody's had had an F3 fault, and they say, "I've swapped the inverter 3 times, and everyone's still got an F3 fault." I said, "Well, why don't you check your solar panels?" F8 fault. So this is actually caused by an error in the control card. It very rarely comes back, but if you ever get an F8 fault, then this is actually one of the few problems we ever get to see with an inverter, and this is an inverter fault. So this is something that it's very fixable. It's very quickly fixable. The service, but it's something that you should come. F10 is internal power supply fault. So inside the inverter, it has its own power supply, because in the inverter you've got your control card, your card with your sort of your intelligent bit, which is like a mini laptop, and you've got your relay card. You've got the various cards, and it's all run from an internal power supply. So this is a power supply fault, and I'm being very transparent here because I'm showing you all of the faults, including what can cause on the inverter, but what can cause external. F13, work mode change. Work mode change is when you're changing the operation of the inverter. It's a massive change on the inverter. And so therefore, if you're changing its function suddenly by programming it, something unexpected, then you may get an F13 because you've done something. And this is normally user error. So when if somebody's touching it and they do something wrong, and suddenly change the way it's functioning, or change the battery, or change something on the programming, then you might hit an F13 fault. but this is nearly always caused by user error and setting the thing up. F18. We always get lots of F18s. It's an error, an overload. Okay, this is an overload. Okay, so often is people take too much power. It's basically an F18. You've overloaded the inverter. Could be a surge. Could be something going wrong on somewhere, but you've overloaded the inverter. A bit like your fuse pops on your thing. This is because maybe somebody has specified the inverter too close. So you've got a 10 kilowatt inverter, and they may take a 12 kilowatt load. Or some people might put, say, a 5 kilowatt and try and get a full house backup. Full house backup draws 20 kilowatt. You switch too many things on, you're going to get an F18 fault. So an F18 fault, and I can put these up, but sometimes it can occur in the night. It's heavy. Maybe you've got a very heavy old-fashioned air conditioner, and sometimes you get F18, you get a surge fault. Some air conditioners, if you switch it off and switch it back on again very quickly, they can have a huge inrush current, especially the older-fashioned ones, the older air conditioners. So it's often air conditioners can cause it, but it's something to bear in mind. F20, DC voltage caused by the panels. So basically F20, you've got one of the panels backwards. It's really simple. That's an installation problem. F23, AC earth leakage, transient current. Okay, this fault is on the main side caused by earth leakage trip from PV. Okay, check your cables and reset your system. This is a fault, this is a solar panel, it's another solar panel one. So if you get F23 fault, F23, it's a solar panel. So just bear in mind this one. F24, earth leak, again, it's solar panel. So it's where the cables may be touching on the solar panel. You've got a problem on the solar panel. F24, it's an insulation problem, but it is a solar panel issue. If you got an F24, you're going to have to get somebody to check your solar panels. So F24 fault, don't run and say, oh, my inverter's faulty. It's an F24, it's a solar panel problem, okay? Internal, but this is an internal one. F26 is actually a problem with the inverter. Again, these faults are really rare. Our failure rate is extremely low. And so, if you get an F26, it is a very, very rare fault. F29, parallel communication fault. Well, F29s can occur in lots of reasons. So basically, if you're paralleling inverters, you've got paralleling working in three-phase, anything goes wrong, any other fault will generate an F29 fault. So it will drop out the paralleling system. So if something goes wrong somewhere on any inverter, on any connection, it will always drop out because the paralleling system will drop out as a safety device. It always does that. F34 overload, F35 no AC grid, F31 parallel system stop check. Okay, F47 frequency, AC frequency. Sometimes this is really, it's not likely to happen on the grid unless you've got a really. If your grid is very heavily subscribed, running off one local power station, it very rarely can happen because the frequency from the grid will very rarely change. If it does change, there's something drastically wrong on your supply. But it's more likely to happen from powering from a generator because when you load a generator up, the frequency can drop a little bit. And by the frequency dropping a little bit can cause this problem. And so you can actually do something on the settings, you can widen it up. If it's on the grid side, then you need to contact your grid supplier because it is a problem. And the same with F48. F55 is battery voltage too high, could be caused by rubbish batteries. The battery voltage is rising too high and you're going to get an F55 fault. That's often maybe cheaper batteries, the charge will take it too high. The BMS is not controlling the voltage. And if you experience F55, change your batteries. This is all I can say is consider the batteries. F56 is generally a battery problem, BMS. Again, look at your batteries, check your C rating, maximum charge, maximum discharge. Most batteries you should be considering running the systems. People say we've got C1. C1 means you can fully charge the batteries and fully discharge the batteries in an hour. Personally, I would never run them at less than 0.5. That means 2 hour maximum charge time. When you go to a C1, all your cables must be thicker, double thickness, double everything, because you're ramming a lot more power into them and taking a lot more power out. If you want for longevity, try to keep it, even if you've got a C1 rated batteries, and some of the Sunsynk batteries are C1 rated, I would still prefer, unless it's absolutely an emergency or certain circumstances, running them at C.5. But you know, an F56 is generally a problem to do with the battery communication. Again, it's the same as F58. F63 is an arc fault, but some of our newer inverters have arc detection. Some of the older ones don't, but again, it's in F64. It's getting too hot. Some people say the inverter's getting too hot. If it's running fine. It will temperature control, the fans will operate, everything else. Only an F64, if you see an F64, then you've got a problem. It will shut itself down. Make sure if the fans are not running correctly, if the inverters are too close, if you've got parallel inverters too close, it's in a confined area, you might start suffering from F64 faults. Phase rotation. You know, this basically is on 3-phase. If you're using a 3-phase inverter or you're using 3 inverters together, you make sure you've got your correct phase rotation. I've got videos showing about that. There's some videos, some very good videos explaining about phase rotation. Somebody says to me, oh, but the local power company, they wired it, but they wired the phase rotation backwards. I doubt it. I personally would never, ever see a grid utility wiring backwards, because that means all the motors go backwards. It's flipping dangerous. So if it's powering into factories, then suddenly all the conveyor belts are going to go backwards. Everything go backwards. So I doubt it. It's more likely a local wiring issue. But please make sure your phase rotation, because your phase rotation going in must be the same phase rotation coming out. And I have got a very nice video when I did it in Hong Kong showing about phase rotation. Right. Yeah. I need a drink, I think, shortly. Coffee. Yeah, commissioning procedures. Well, yeah, this is something interesting. You know, some people wire all it, this is your boop, 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 boop. You know what? That's not so clever. It's not the clever way to commission an inverter. You need to consider a much better way to commission it. And this is sort of a very simple way. Okay. So before switching on the installation, an engineer must complete the earth bond and make sure all the tests are correct. They've got to do all your legal tests. So the electrician must check and make sure you've got your earth continuity, your earth bonding, everything is correct. You must do all of the legal stuff, and that must be done by a licensed contractor. Check your voltages, your solar panels don't exceed. I put 450, 480 maybe, okay, but make sure about, check your battery voltages. Where parallel says, check everything, you know, check before you switch anything on, because if you get some of this wrong, you're just going to blow it to pieces. You know, these are very simple tests, but these are things you must do before switching it on as part of your commissioning process. Right, okay, well, this is something that somebody did for me. If using more than one battery, check they communicate with each other. Switch on the battery. Switch the batteries on first. If you've got battery inverter, power from your batteries. Don't power from your mains, power from your batteries first. Check your communication is good from your battery. I'll put this slide on, I'll put this on the notes for this video, because it's a really useful slide. It's a bit like airline pilots. We've got these sorts of, if something goes wrong, they'll check the line cards, they'll check their written manuals, check the manual. This manual is great. This is really important. Check this communication of the batteries. Wait for the normal light to appear. It could take 5 minutes. You know why it takes? Because I said before, it's synchronizing the inverter with the grid. So you wait for your normal light to come on. You're running off your batteries, your communication, okay? So basically you're checking go through your screens, check your systems. After the normal light, switch, right, when your normal light's on, next thing is turn your PV on. So first of all, you're running from the battery. Next is your PV array, okay? everything's running, when everything's running nice, you do it by sections, because if you've got a problem somewhere, it will highlight it. What you don't want to do is go boom, 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 switch everything on and sit there, it's not working. Do it this way and you know everything is good, safe. And it's a nice feeling, because when you're running from the battery, inverter's running, it's running perfect, got normal light, everything is working perfectly, okay? Wait, just wait a minute, make sure it's all, just sit down, wait. It's too tempted. Check everything, check everything, check everything. Check all your systems. Finally, down here now, switch on your AC. Do all this first. Don't put your AC on at the end. Put your AC. Check your CT coil is working at this point. Make sure your CT coil is not running negative. It's running the right way. Check your CT coil. Finally, when it's all on, check all your systems again, check all your settings again, check and check. But the most important thing, if you get anything from this video, if you watched it to this point or you haven't switched it off, I'm talking to myself. But the most important thing is go through a nice commissioning process. Run from the batteries, put your solar, bring each part in slowly, and this is a much better way of doing it. Checking your batteries are communicating. Nowadays, it's less of a problem. Before, we used to have lots of issues, but nowadays, everything is very simple. It's all plug and play. So it's less of a problem. We used to have lots of issues with batteries because batteries used to all use lots of different protocols. Most of them have common protocol. There are a few odd ones, but if you use an approved battery, or if you're using a Sunsynk battery, then you're never going to get a problem. You'll never get an issue or whatever. You're checking the communications, the batteries, make sure your batteries are working correctly. So as I'm going before, you wait for your normal light on your inverter. Once you've got your normal light, you know everything is functioning. You know the inverter is working, everything is hunky-dory, it's running from but just check everything very carefully. Because when you put your AC, suddenly you might get a trip. You know it's nothing to do with the inverter, it's something else. So you have to check everything very, very carefully. Check all your AC batteries, all your systems here, your frequency. Nowadays it will default because then many years ago we had to set everything manually. Now you will set your NRS standard or your G98, G99 standard, and everything. All this is done automatically for you. You've got your your up and lower your frequencies, your voltages. It all comes part of the regulations. So nowadays you don't need to touch any of this. You used to do this a long time ago. So you can actually see from, if you actually touch the if you actually touch the screen, you will see the flow. But always, I said before, wait 10 minutes. Wait 10 minutes before putting the AC. You say, why? What's the point? It's a nice time. You know everything is good. You know nothing's gone wrong. You sit comfortably. Go and have a cup of tea. Come back. So right now, put the AC on, and you'll feel much more comfortable because you know it's going to work. Then put your AC breaker on. Finally, God, that's me a few years ago, connecting a generator on a site. And finally, you recheck all your systems, check everything again, and that's it. So I'm going to close that off now. And that was my presentation from a couple of years ago. I decided to record it because I thought it might be useful, or somebody might want something to watch before going to bed, or if you're on an aeroplane, download it on YouTube. Maybe it's something worth watching. You'll get a basic understanding. I'll put some of the other files onto this, but this gives you a basic understanding about the inverter, about using it, about the MPPTs, the voltages, and how the inverter works. So I hope it's useful. And the weather's beautiful. Oh God, it's lovely. It's a bit cold, but it's lovely. I was saying in the presentation, why do I talk about the weather? Well, I'm English, and being British, we always talk about the weather. So yeah, thank you for following, and please subscribe. Any suggestions for other videos, please let me know and I'll do them. But as I say, I hope it's useful. Thank you very much for following.